Thank you for joining us on our 22nd Classical Mechanics 1 meeting at CMI. Today is Thursday, the 9th of December 2021. Yeah, so I was just generally discussing with those who are already present about the state of the semester and the challenges that you may be facing. I do realize that you have a lot on your hands. I do bear that in mind. And if you have any specific feedback concerning this course, you're welcome to tell me about it. I mean, either here or by email or any other means. Yeah, any questions before we continue?
Sir, could you elaborate on the grading metric?
Grading
like the final grade, not assignment wise, but like fine totally. Like how do
grading
the weightage of assignments or like mid sem, end sem, sorry.
Yeah, it will be. Yeah, we will have some more thing for you to do, which will count as the end sem exam, and that will be given its due weightage according to the rules. Yeah, this course is not so the homeworks that you have been doing play a very significant role, and I am pleased that many of you have put a lot of effort into it, and you will be justly rewarded. I don't have if you have worked hard so far, I think you can be happy. You should get a decent grade. I think beyond, but okay. Siddhant, is there something more specific you are asking?
No, sir. Because each individual assignment has a different level, different marks. Like total marks of each assignment is different.
Slightly different. Yes.
Like 15 to like 23. That's the range.
Correct.
So I was wondering if like each assignment gets equal weightage or like the weightage is like weighed like according to the marks.
The weightage is according to the marks as already given. That is, yeah. Yeah, roughly, we are not going to reweight one assignment as more than the other, unless there's a very specific reason to do so. And no. Yeah. It has been a continuous assessment of things, and we have not conducted any quizzes, and I have not specifically planned such a thing.
Okay, sir.
Yeah, that is not to say it will not happen.
Okay, sir. Thank you.
Yeah. So my advice to you is don't worry about Classical Mechanics 1. Enjoy the ride through special relativity that we will begin today. Learn some physics. If you have been working sincerely over the last 2.5 months, you are in good shape. Don't worry beyond that. There'll be a little bit more work to do in the coming 2-3 weeks, and then we will have a nice break. Okay, so let us begin a new topic now. Okay, so let me share my screen. Yeah, so I intend now to discuss a new topic, namely a few things concerning special relativistic mechanics. Now, this is a continuation of what we have been doing. So you will see similarities with the concepts we have already introduced. And it will build on those things. Now, we begin with certain difficulties with the Newtonian mechanics. Yeah, But I must preface all of this by saying that Newton mechanics is an excellent framework to do physics, mechanics, and it has certain shortcomings, but it is a very, very wide applicability and continues to be the main predictive framework for much of our scientific work. Yeah, but it does have certain conceptual shortcomings and as well as experimental shortcomings, which we will discuss now briefly. Yeah, so let me begin with certain difficulties with Newtonian mechanics. So Newton, in his formulation of mechanics, as we have pointed out earlier briefly, in effect postulated that all observers, all observers, and here all observers really means not necessarily ones who are moving at constant velocity relative to an inertial frame. Basically, every observer, irrespective of their state of relative motion, could synchronize their clocks to a common time and could agree about the simultaneity of a pair of events. Okay, so this is something that has gone into, we have mentioned it before. And I will say a bit more about this. So basically, there is a common time that everybody could have. Even though your clock may be slightly different from mine. Okay, let us suppose we all have identical clocks. It is possible to synchronize those clocks so that we agree on when a certain event happened. And if two events I say happened at the same time, you will agree with that. And this was basically what Newton assumed. Now, in the late 1800s, Ernst Mach, by the way, Mach is from which place or which country? Do you have some idea? Yeah, you're right. He's Austrian. Yeah, Austrian physicist and philosopher. Ernst Mach criticized this postulate as it was not backed by an examination of the physical processes involved in measuring times using clocks carried by various observers. Okay, so a detailed study of that had not been made. And Mach, in his book on the science of mechanics, raised certain criticism on Newton's assumptions. Nevertheless, Newton's assumption about time remained at the foundation of mechanics for nearly 200 years, since the late 1600s till the late 1800s, since its consequences were largely in agreement with empirical observations. Okay, so that is the gold standard, and since those assumptions were not seriously violated, I mean, the consequences were in line with observations, it was reasonable to retain them. However, things had begun to change. And just to say in a few words, with the benefit of hindsight, we may say that the Newtonian assumption about a common time for everybody, all observers, is a good approximation as long as speeds of particles or of observers, and here it is relative to an inertial frame, I will be more precise about these things, are much less than that of light. Okay, so the Newtonian assumption about a common time and synchrony of clocks, is something that is a good approximation as long as speeds of particles and observers are much less than that of light. With the benefit of hindsight, we can say that. And in effect, Newton had assumed that light traveled infinitely fast. Now, based on this statement, it is perhaps not a surprise that difficulties in the application of Newtonian mechanics first arose in matters concerning light, because it was light regarding its speed that Newton had made an assumption which was called into question. So difficulties with Newtonian mechanics first arose in matters concerning light. So what are those difficulties? So first, by the 1800s, there was strong empirical evidence that light traveled at a large but finite speed, which now is roughly 3 times 10 to the power of 8 is our reasonable value, meters per second in vacuum. So this was the experimental evidence that light is not infinitely fast. Now, but there were other issues also. One moment, I'm just. Yeah, okay. So next, aside from mechanics, the other pillar of physics was electromagnetism, among other things. I mean, there are other subjects like elasticity and thermodynamics and so on. But Maxwell's equations of electromagnetic phenomena had been hugely successful in understanding electricity and magnetism. Yeah, so this had been developed over the course of the 1800s. I mean, it was culmination of efforts of many people, but in this last phase, it certainly was from Faraday to Maxwell. And these equations predicted that electromagnetic waves, I mean, which you will read about in your electromagnetism course later on. This included light. Electromagnetic waves included light or visible light. Yeah, they predicted that light and electromagnetic waves must travel at the same fixed speed, which we denote c, in vacuum without regard to the motion of the source or observer. Okay, so this was a result from electromagnetism. Now, there was a little problem with reconciling this with mechanical principles. Now, we will elaborate on this. One second. Yeah. Yeah. So other types of waves known at that time, I mean, other than electromagnetic waves, such as sound, yeah, or waves on the surface of the ocean, sound waves, or waves in elastic media, earthquake waves, all these things. Yeah. In all these cases, these other types of waves known at that time were traveling disturbances in a medium like air or water. Okay. So this was a common feature of waves known at that time. And in the case of these waves, like sound waves, the observed speed of sound depended on the motion of the observer through the medium. Okay, so we will say later on precisely how. Yeah. So, I mean, if you are moving towards the source of sound, yeah, so the speed of that sound wave appears different than if you are stationary. This is the kind of thing I'm talking about. Whereas on the other hand, the speed of light as determined through Maxwell's equation did not seem to make any reference to the observer's motion. Yeah, and moreover, based on the analogy with sound, which was one of the best understood waves at the time, it was assumed that light waves too must travel in an as yet unobserved medium. So it was assumed that just like sound waves are vibrations of a medium like air or water, it was assumed that light too must be some sort of vibration of some medium. But that medium had not been found, so it was some as yet unobserved medium, which was called ether. Yeah, so it was presumed that this ether was an all-pervasive thing that was all around us. Yeah, but ether had to have some peculiar properties. Yeah, on the one hand, to allow light to travel very fast, yeah, it had to be minimally deformable. It had to be very rigid. Yeah, I mean, this again by analogy with sound. Yeah, because sound travels faster in a rigid medium like a solid than in a gas. Yeah, you can hear the approaching train more slowly later on in the air than if you put your ear to the train track. You can hear it earlier. Yeah. So this medium, whatever it was, which was called ether, had to be very rigid to support a very, very fast moving wave. However, it had to be very rare to have evaded detection through its effects on the motion of planets, yeah, or even of projectiles and other things. So it had to have these somewhat disparate properties. One, it had to be very rigid for the light to travel very fast. It also had to be very, very rare because we have not even found it yet. Yeah, it had not been detected at that time. Now, Albert Michelson, American experimental physicist, set out in the late 1800s to detect the effect of the motion of an observer through the proposed ether medium on the observed speed of sound. Okay, so just like the speed of on the speed of light. So just as the speed of sound depends on the motion of sound, the medium depends on the medium. Yeah, I mean, the speed of sound is different in air and water and so on. So he set out to find out this effect of the motion of an observer through this ether medium on the observed speed of light. Okay, so that was his objective. So he used an instrument called an interferometer, which is a very clever instrument. I'm not discussing it in any detail here. I'm not going into that right now. Maybe sometime later, or you can look it up. So using what is called an interferometer, it is basically based on the principle of interference of light that is made to go through two different paths, and light waves can be made to interfere, and by looking at the pattern of interference, one could find out about this relative motion and the speed of light. Yeah. When it passed through different through the medium in different ways. So using an interferometer in 1881 and later along with Morley in 1887, Michelson and Morley obtained a null result. And what does this word null result mean? The phrase null result means that from their experimental observations, the speed of light was the same for a variety of observers moving differently through the ether. Okay, so we are supposing that the ether is present, yeah, and then you move through the ether in different ways, and those different ways were achieved through the rotation of the Earth. So because the Earth rotates, and you can achieve different directions of motion and so on. So the rotation of the Earth altered the direction of motion through the proposed ether. At least if there was an ether, that would be the case. And they found that this had no effect on the measured speed of light. Now, this seemed to be at odds with expectations based on Newtonian mechanics. I will elaborate on that, but I'm just giving the overall historical information. Yeah, so the null result of Michelson and Morley was inconsistent with expectations based on Newtonian mechanics, which said that the motion of the observer through the medium would affect the perceived speed of the wave, in this case light. Now, attempts were made to explain this null result by many physicists, as well as mathematicians or mathematical physicists, but they often seemed a bit contrived, somewhat artificial, but they involved very clever ideas also, and some of them were eventually resurrected and could be very useful. Yeah. So they typically introduced other complications, so that was a difficult issue. For instance, Fitzgerald, Irish physicist, and Lorentz is Henrik Anton Lorentz. I'm sure you heard the name. We have talked about the Lorentz force. Yeah. I just wanted to pay attention to the spelling of the name, Lorentz. There is also other Lorentzes in physics where the T is missing. So just be aware of that. They are different people. So Lorentz is from which country?
The Netherlands, right?
So correct, you are right. That is that Gautam Vishwanathan.
Sir, you confused us again.
Oh, I'm sorry. This is Anand Balivada.
Yes, sir.
I am sorry. I am very sorry. Yeah, I am using my.
It's totally fine, sir. It's okay.
Okay, fine. Anyway, Hendrik Anton Lorentz was from the Netherlands, Leiden, a very reputed physicist from the Netherlands, and very respected physicist. These people proposed that the motion through the ether produced just the right contraction. So an interferometer has sort of two perpendicular arms, and light is sort of split into the two arms of the interferometer and then goes around and joins, and the beams are made to interfere. So there are two arms of this interferometer. Or it may also be reflected and brought back instead of going all the way around. May have just two arms where it goes in one arm and gets reflected, goes in this arm and gets reflected after being split, and then you interfere the reflected beams. So so they propose. I mean, the details of this are interesting, but I think right now is not the time to discuss them. I think one has to take a course in waves also and light and so on in electromagnetism. So I don't intend to do that. I want to give the overall picture and what the result was. So they suggested that to explain this null result, assuming the ether is present, they suppose that one arm of the interferometer had to reduce in length because of the motion through the ether, in order just to cancel the effect of the change in speed of light due to the relative motion. Okay, so so they propose some scheme by which you could explain this null result. One of the arms of the interferometer had to contract so that the change in the speed of light would go undetected. Yeah. In fact, even yet more clever ideas were proposed, no less than by Henri Poincaré. I don't know if I have mentioned Poincaré here before, but where is he from?
France.
Yeah, Poincaré was a French mathematician and physicist. So Poincaré suggested that, among other things, he did a lot of very important work. He was very proud of being a miner. He was a mining engineer, but he revolutionized mathematics, among other things. So and also celestial mechanics, classical mechanics, etc. So among other things, Poincaré suggested that ether is there, but no experiment can detect it because the effect of ether will be cancelled by some kind of equal and opposite effect. Yeah, so this was some kind of analogy with Newton's third law, where some force has between one body and the other has a reaction force, the reversed pair. So by some analogy to that, he suggested that though the ether is there, the effect of the ether is always cancelled by some equal and opposite effect. Yeah, something to that effect. So a lot of people thought about this and tried to find ingenious ways to accommodate the ether. Yeah, and in the process produced very interesting schemes, which one can study and read about. But the situation was rather confusing and vexing. In 1905, Einstein brought clarity to this confusing situation when he introduced his special theory of relativity. So we will now talk about that, the key concepts. Now, Einstein said that he was not influenced by the null result of Michelson and Morley. And that is because, according to Einstein, he said that he had already come to the same conclusion, similar conclusion, that the speed of light is not dependent on observed motion through medium. Yeah, he had come to a similar conclusion based on earlier experiments by Hippolyte Fizeau, 1851 experiments that attempted to detect the effect of a moving medium namely water and air, on the speed of light. So Fizeau had found an unexpectedly small effect in water and no effect at all in air. Okay, so these were more primitive experiments compared to the interferometric experiments of Michelson and Morley. But nevertheless, Fizeau had found basically no effect in air and very little effect in water. So Einstein was already aware of this, and he had taken that quite seriously. Now, Einstein was also influenced by Mach's critique of Newtonian mechanics. On the one hand, you remember Mach had criticized that Newton hadn't seriously looked into how do people synchronize clocks. I mean, how do they send signals to each other and so on. Yeah, so Einstein was influenced by those thoughts and criticisms. And he was also strongly influenced by Maxwell's electrodynamics, which I will speak about in a moment. What I've already mentioned, that Maxwell's electrodynamics predicted that the speed of light is independent of the motion of the observer. And now Einstein's insight was rather bold insight, but also very conservative viewpoint. Yeah. So what was Einstein's basic insight? His insight was that the principles of Newtonian mechanics, which were so well tested and assumed to be good and reliable, but since there were contradictions with phenomena involving light, his insight was that the principles of Newtonian mechanics had to be revised so as to make mechanics compatible with Maxwell's electrodynamics, right? So this was his viewpoint, and to avoid the contradictions in interpreting phenomena involving light. So Einstein suggested that it is Newtonian mechanics that needs to be fixed. Now, special relativity is based on a pair of postulates, and the word special has to do with the restriction to inertial frames. Okay. So when we use the term special relativity, the word special means we are talking about physics viewed in inertial frames of reference, and inertial frames are what we have understood. Newton's first law defines inertial frames as a frame in which an otherwise a particle that is not under the influence of any other physical bodies would travel in a straight line at constant speed. So that is what an inertial frame is. So special relativity has to do with physics in inertial frames, right? We can ask about other types of frames like accelerated frames. Special relativity is not concerned with that. Okay. So special relativity, I mean, you will see the reason for the name relativity. Yeah. I mean, in brief, it has to do with things like simultaneity and other concepts being observer dependent relative to an observer, and that is where the word relative comes in. Yeah. I mean, it doesn't mean everything is relative. Okay? There are some things that are relative to an observer and so on. But anyway, the word has become quite standard. It's based on a pair of postulates. One is called the principle of relativity, and the second is the constancy of the speed of light. So let us state these two postulates. Now, the principle of relativity is familiar to you because we have talked about it, and it goes back to the 1600s. It goes back to Galileo, who had proposed it in the context of mechanics. Right? So let me just remind you that Galileo had pointed out that there is no mechanical way of determining whether an inertial frame is at rest or in uniform motion. Okay, so there is no concept of absolutely at rest inertial frame. Yeah, a ship in the dock and a ship moving uniformly at sea inside these two ships, if you do experiments without access to external influences, like some external electric fields and external gravitational fields and so on. Though he was mainly concerned with mechanics, so he was concerned with mechanics, you cannot tell whether you are in the moving ship or in the stationary ship. Now, Einstein argued that this Galilean relativity principle must apply not just to the laws of mechanics, but to all the laws of physics. Okay? In other words, what he says, Einstein postulates, is that if a law holds in one inertial frame, a law of physics. Okay? I must emphasize that a law of physics is different from, not everything is a law of physics, right? So saying that the position of the particle at this instant of time is 2 meters in some coordinate system, that's not a law of physics. Okay, that's not a law of physics. You cannot say that that law should hold in every frame or something like that. That is certainly not what we are saying. When we say law of physics, we mean things like Newton's second law, Newton's first law, these kinds of things. So because I have noticed one or two some confusion in that. You cannot take any statement and say it's a law of physics and so it cannot change when you go to another frame. That is certainly not true. So Einstein argued that Galileo's relativity principle, that the laws of physics are the same in all inertial frames, must apply not just to the laws of mechanics, but to all the laws of physics. Okay. So if a law holds in one inertial frame, it must also hold in any other frame moving at constant velocity relative to it. Okay. So that is the principle of relativity extended by Einstein from mechanics to all the laws of physics, in particular also to electromagnetism. Now, what is one immediate consequence of the principle of relativity is that accepting the principle of relativity meant discarding the ether hypothesis. Okay, because if you accept the ether hypothesis, the ether is some sort of medium. If you accept it is there, then there would be a distinguished inertial frame which is at rest relative to the ether. Okay, so it was hypothesized that the ether is like some liquid or something, or like water or something that is there out there, which is very rare but very rigid. But anyway, whatever it is, there would be some frame that is at rest relative to that ether, and that would become a distinguished frame. But Galileo doesn't permit such a distinguished frame. So accepting the principle of relativity meant discarding the ether hypothesis. Okay, so let us see what else and why he did this, why he proposed this. Now, it is because the failure to detect motion relative to the ether, the failure by Fizeau as well as Michelson and Morley, they failed to detect motion relative to the ether, suggested that it was more economical to discard the ether concept and retain the principle of relativity. Okay, so Einstein took a very conservative viewpoint that the experiment is not giving any detection of ether, so why not throw it out? That's all. But it's not so easy, because there is a problem with the Galilean principle also. That also has to be slightly modified, how it is implemented. So we will come to that in a moment. Okay, so first postulate of Einstein is that we accept the idea that if that law of physics, if it holds in one inertial frame, it must hold in any other inertial frame moving at constant velocity relative to it. And this must apply to all laws of physics. So, okay, now moving on from the principle of relativity, let us now speak about the second postulate. We come to that. Moreover, Maxwell's equations, which we have not studied, I'm just stating, predicted a universal speed for light without reference to any medium. So the simple interpretation of this, though not so simple at the time, was that there was no role for ether in electromagnetism. Okay, that was the simple interpretation that Einstein championed. I mean, you must see the inertia in this. Yeah, even Maxwell himself, by inertia, I mean the reluctance to drop ether. Yeah, Maxwell himself believed in ether, though Maxwell wrote down his equations, he still believed in ether. Yeah, so there was a lot of reluctance to drop ether. Yeah, uh, partly because of physical experience that all waves move through some medium, so this too must move through some medium. The acceptance of the medium should be present. That was a very ingrained tendency. So it was hard to drop that. So Einstein's proposal is that there is no role for ether in electromagnetism. Now, this brings us to the second postulate of special relativity. Yeah, that the speed of light in vacuum is the same constant c in all inertial frames. So this is the postulate of second postulate of relativity, that the speed of light in vacuum is the same constant c in all inertial frames. Now, this is a truly a bold proposal. I mean, if you have a sound wave and it is going from here towards the next building, and I myself am walking towards that building, then the speed of that sound wave is actually less relative to me as compared to relative to the ground. Okay, that is what Galilean relativity tells you. The Galilean velocity addition formula tells you that the relative velocity between the sound and myself is actually less than that between the sound and the ground. Yeah. So basically, Einstein is saying that doesn't apply to light. The speed of light relative to the ground and relative to me who is running are one and the same. This is the proposal of Einstein. And his reason for proposing this is that Maxwell's theory predicted a constant speed of light independent of the motion of the source or observer. Yeah. If you have an antenna, which is some charged particles which are shaking, producing some waves, electromagnetic waves, the speed of those waves don't depend on whether that antenna is at rest or itself moving and such things. Okay, so so based on that, Einstein proposes that the speed of light is independent of the motion of the source or observer. And also in Maxwell's theory, it had no reference to any medium. So Einstein postulated the speed of light must be the same for all inertial observers. Okay? And that includes observers moving in different directions or people who are rotating their frame. Yeah, just turning my head, the speed of light in this direction and that direction are one and the same. Yeah, so speed of light is independent of direction and independent of motion relative to the observer or the source or the medium. Yeah. So we have made stated two postulates of relativity. They're really very simple. One is that physics principles should be the same in two frames that are in uniform relative motion. Yeah, this is a very simple proposal, which is basically what Galileo said. Simply extend it to all physical laws, not just mechanical laws. And the second principle is that speed of light is the same constant in all inertial frames, no matter whether the frame is moving, fixed, etc. Yeah. In other words, the analogy with sound waves, which require a medium for their propagation and whose speed depends on the motion of the observer and source, has its limitations. Okay, so it is true that the analogy with sound is very helpful, but it has its limitations and we have to be aware of that. Now, again, let me emphasize that these postulates seemed to be the simplest way to accommodate the available theoretical knowledge. By that, I mean, by theoretical knowledge, I mean the constancy of speed of light in Maxwell theory. Yeah. And the other theoretical knowledge was the absence of any distinguished frame in Galilean relativity. Galilean relativity does not permit any distinguished inertial frame. Okay, so if you are willing to accept that and want to retain that, which is a very successful principle, and you want to also admit in Maxwell's laws saying that the speed of light is a constant, then the simplest way to do so is to accept both. Yeah, and it was also the simplest way of accommodating all the experimental and observational data namely from Michelson's experiment, that the speed of light is independent of the observer. Yeah, and also that experimentally the ether had gone undetected. So this undetectable medium maybe has simply to be discarded. Okay, so this was the simplest way of accommodating both the theoretical knowledge and the experimental data. Yeah, now now, though it's not stated as a postulate, I would also like to mention that in addition to these two postulates, Einstein was strongly guided by what one might call the correspondence principle, which is a very, very important principle in physics. Which distinguishes physics from certain other disciplines, that the relativistic generalization of the laws of mechanics, the relativistic generalization of laws of mechanics, namely Newton's laws, Newton's first law, second law, yeah, whatever their relativistic generalization are, must reduce to those of Newton when the speeds are small compared to that of light. Okay, so Einstein may be proposing some revolutionary ideas, but whatever those ideas may be, when you apply them to situations where speeds are small compared to that of light, all your predictions must reduce to those of Newtonian mechanics. So that is the correspondence principle. There must be a correspondence between the slow speed limit of relativistic mechanics and Newtonian mechanics. Okay, so this is the correspondence principle. And there's one more aspect to it, that the rules for transforming physical quantities between inertial frames. Okay, so you have two inertial frames. We have spoken that like the position coordinate is given by a rule for transformation. Yeah, suppose you have two frames here, one is S, one is S prime, and S prime is moving at some velocity V relative to S, then the position vector of a particle relative to the S prime frame. So you have a particle which is instantaneously located at R prime. Yeah, the position vector R prime is related to the position vector R through a certain transformation R minus Vt. Okay, so this is called a rule for transforming a physical quantity between the two inertial frames. Okay, so this is the Galilean transformation of position vectors. Yeah, between S and S prime. Now, this cannot be retained in relativistic mechanics, unfortunately. That has to be, this is a transformation rule has to be changed. We will explain why. Yeah, but whatever change you propose in it, in the limit where V is small compared to C, yeah, in magnitude, whatever that new transformation law is, must reduce to the Galilean transformation law. Okay, so this is again correspondence principle, that the new transformation law in the limit of slow speeds must reduce to the old transformation law. Okay? So this is a very important part of physics, where the existing framework is not completely wrong. Yeah, it has already been tested in many situations. So in those situations, your new framework must reduce to that. Right? We are not overthrowing everything. So it puts a very strong constraint on some newfangled theory. It must agree with the predictions of the old theory in the domain of applicability of the old theory. Okay, so this is called the correspondence principle. Now, the name correspondence principle was actually coined somewhat later, was introduced by Niels Bohr in postulating that the laws of quantum mechanics must reduce to those of classical mechanics in the limit where classical mechanics holds, okay, which is more precisely, it is the limit, it's called the semi-classical limit of large quantum numbers, yeah, where quantities with dimensions of action are large compared to Planck's constant. Yeah, so there is some limit where quantum mechanics should reduce to classical mechanics, and that is the principle that the results of quantum mechanics should agree with those of classical mechanics was called the correspondence principle by Niels Bohr. Yeah, and a similar principle must apply also in relativity. That is what Einstein said. I mean, Einstein's proposal came much before Niels Bohr, but the name we are borrowing from Niels Bohr. Yeah, so we have just now mentioned the postulates of the special theory of relativity. Okay, some noise. Somebody.
Sir, I have a question.
Yes, may I know who is speaking?
Sir, Rajdeep.
Okay, Rajdeep, yes.
So my question was that I don't know why it feels like the two postulates that Einstein put forward are in somewhat contradiction of each other. Because if I had a frame, which
No, wait a minute, let me just understand. Are you saying that they contradict each other, the two postulates?
it seems like they contradict each other in certain scenarios.
Okay, yeah, fine. Yeah, sure. They will contradict each other within Newtonian mechanics. Within Newtonian Galilean relativity, you will find contradictions if you try to impose these. But please go ahead.
No, so I was just thinking of a very simple scenario. That if I had a frame, which is my frame one, in which there was a beam of light moving at speed c,
Okay.
I considered another frame,
Yeah.
which was at say some speed v with respect to the first frame.
Yes.
Then the Galilean transformation dictates that the speed of light should be
yeah, c minus v.
yeah, but that contradicts the second postulate.
Exactly. So you have pointed out a very good thing. So what is the problem there? The problem is uncritical use of this Galilean transformation law. We have to throw out the Galilean transformation law. Simple as that. The formula saying that v prime is equal to v minus c. Sorry, yeah, whatever you said, yeah, that the speed as seen in a moving frame is the speed in the original frame minus the difference in the speeds of the frames. Okay, we are having some serious problem with Rajdeep's audio. Okay, I have muted Rajdeep. I will unmute you in a moment. Once I finish speaking, then you can come back. Or you can unmute yourself. So you have pointed out that Galilean transformation rule for velocities between moving frames, between frames in relative motion, is incompatible with constancy of speed of light. This is absolutely correct. Yeah. So we cannot take the Galilean transformation rule into special relativity. That is the conclusion. In other words, the formula which I have highlighted here does not hold in special relativity. Yeah. In particular, if you differentiate this thing, you will get r prime dot is equal to r dot minus v. This formula for transforming velocities does not hold in special relativity. That is the conclusion. Okay, so you are happy with this for now?
Yes, sir.
Yeah, excellent. Yeah, but you pointed out a very good thing. Yeah, what we have said through the correspondence principle is whatever this law is going to be replaced with, this transformation rule is going to be replaced with a new transformation rule. Anticipating its name, at least I will call it the Lorentz transformation rule. That transformation rule will be constructed in such a way that it respects the constancy of speed of light in the two frames. Okay, so that is how it will be constructed. And to this new transformation rule, when this speed v is much less than speed of light c, will reduce to the Galilean transformation rule. Okay, so these are the two constraints we will impose on this newfangled transformation law. Is that okay? At least
simultaneously
yeah.
Is like if two events are simultaneous in one inertial reference frame, then any frame moving with constant velocity, will both of them be simultaneous in that frame?
No, not if the speed of light is finite. In special relativity, that concept of simultaneity unfortunately does not apply anymore. It is true only in the limit when speed of light is assumed infinite. We will come back and explain how it is violated. So simultaneity is becoming relative now. So we can speak of simultaneity relative to a frame. And two events that are simultaneous in my frame need not be simultaneous in the frame of a moving car. Is that okay? I forget who asked. That was Bijay and Rai, am I right?
Yes.
Okay, yeah. So we're going to speak about simultaneity, but in brief, simultaneity in the sense of Newton no longer holds. Okay, so very good questions raised by all of you. Let me now do precisely what Rajiv Ghosh was asking.
Excuse me, sir.
Sorry. Yes, please. Shubham Kumar, yes.
So before we move forward, can you explain the last point once again?
About the correspondence principle.
Yes, sir.
Yes. So the correspondence principle is something very special to physics, where we say, okay, we have some old theory, yeah, old framework. Now, due to certain reasons, that old theory has been tested, works.
Sir, I get that point. I
Okay.
want to know about the semi-classical limit of large quantum numbers where quantities with dimensions of action are large.
Oh, okay. Oh, that point. Okay, fine. Yeah. So in any case, yeah. So anyway, there is a framework called quantum mechanics where there is a new physical constant called Planck's constant h bar that plays a role. Now, the idea is that you may be studying certain physical quantities. Suppose you are studying an atom and you are studying the energy of an electron in an atom. Now, the statement is that the properties of that atom in the limit where certain quantities associated with the electron, the action of the electron's orbit or things of that sort, if you can try to make sense of such things, if they are large compared to h bar, then the classical predictions for the behavior of the electron should match the quantum mechanical prediction. This is the statement. So h bar is a constant which has dimensions of action. Yeah, when I say action, it is dimensions of angular momentum. Okay, let me just say it is position times velocity, sorry, momentum. Yeah, position times momentum. So h bar has so it's measured in joule seconds. It has certain value. Now, in your quantum mechanical system, suppose you have a quantity with dimensions of action and its numerical value is large compared to the numerical value of h bar, then you might expect that those phenomena would be well approximated by classical treatment. This often happens when the quantum numbers describing those quantum states are very large. Okay. Yeah.
Okay.
Okay. So without studying, so okay, just to add one more remark, in the context of an atom, where would this apply? The context of an atom, we would say that the very highly excited states of the atom, yeah, where the energy of the electron is very high, those states, the phenomena in those states may be well approximated by the classical treatment of the atom. And Bohr very successfully used this principle in constraining the laws of quantum mechanics as they were being developed. And Einstein did a similar thing a few years before in developing special relativity. Okay, so let us then now come back to what I think Rajdeep Ghosh was talking about, namely the incompatibility of Galilean transformations with the constancy of the speed of light. Yeah. So I want to make a distinction between Galilean principle of relativity. Yeah, this is sacrosanct. This is being held to be true also in relativity, in special relativity. We are not throwing that away. The Galilean principle of relativity simply states that a law holds in one inertial frame if and only if it holds in another inertial frame. Okay, law of physics. Yeah, augmented by Einstein. I mean, I should write here law of mechanics, but augmented by Einstein, it's law of physics, holds in one inertial frame if and only if it holds in another. Yeah, this proposal is carried over to relativity. We are not throwing this away. What we are throwing away is the rule for transformation between frames in relative motion. That is called the Galilean transformation formula. Yeah, with this playing an example role. This is an example of a Galilean transformation formula. How do you relate physical quantities in two frames in relative motion? That detailed formula has to be revised. That's the conclusion we are going to draw. Yeah, we are not throwing away the Galilean principle of relativity. Okay, so I will just repeat what I discussed with Rajdeep Ghosh now, but giving a little bit of framework. So to describe events, an observer finds it convenient to set up a coordinate system or frame of reference. Yeah. So like we said last time, we have the idea of a frame of reference, which for our purposes, you can think of as a triad of mutually perpendicular axes and some notion of time. Yeah. Now, within this Cartesian system, which defines a certain frame of reference, we are then free to change coordinates also from Cartesian to polar coordinates, but within that frame. Okay, so it is convenient to set up a coordinate system within a frame of reference S. Now, for simplicity, we will consider Cartesian coordinate systems for space consisting of an origin and a right-handed frame XYZ axis, frame of XYZ axes. Okay. Now, in Newtonian mechanics, any event is then specified by the time at which it occurs along with the XYZ coordinates of the place where it occurs. Okay, so that is what we understand by an event, referred to a frame and a coordinate system in that frame. Now, Galilean transformations, what are they? Consider an inertial frame of reference S, where the coordinates of an event are labeled T, X, Y, Z. Then, according to Galileo's principle of relativity, the laws of physics must take the same form in S as they do in a frame S prime moving uniformly relative to S. Okay, so that was Galileo's principle of relativity. Well, augmented by Einstein, yeah, because I say laws of physics. But maybe I can restrict to mechanics here if I say Galileo. Now, let us denote the coordinates in frame S prime by T prime, X prime, Y prime, Z prime. Okay, so these are the coordinates of an event. And we can ask, how are the coordinates of an event referred to the two systems related? Okay, what is the transformation rule? We have already seen this, and I wrote it above already today. In Newtonian mechanics, the transformation rule is very simple. First, because Newton says we can all synchronize our clocks, there is a common time for everybody. So T prime is equal to T. Okay, after you synchronize your clocks, T prime is equal to T. Now, for simplicity, we will suppose that S prime and S coincide at T equal to 0. Okay, so at T equal to 0, they coincide, S prime and S. After some time, they may not coincide. S prime may have moved somewhere else. Yeah, maybe at some velocity V. So for simplicity, we will suppose that they coincide at T equal to 0 and that S prime moves at a speed V to the right along the X direction. Okay, so let us suppose it's this way. Then the coordinates of the event T, X, Y, Z. So there is some event. Yeah, so it happens at some time T at location X, Y, Z in frame S. When viewed from S prime, the coordinates are given by T prime equal to T because times don't change, and Y prime equal to Y because the frame is only moving along the X direction, Z prime equal to Z, and X prime is equal to X minus VT. Okay? I mean, that is easy enough to see from here. We have even used it before, that the coordinate relative to S prime, the X coordinate relative to S prime and relative to S are different and they differ by this Vt factor, Vt difference. Okay, so this is called a Galilean transformation. Yeah, or boost by velocity Vx hat. Okay, so we have the Galilean transformation. Now, we observed in our early days of this course that Newton's second law between, Newton's second law is invariant under such Galilean transformation. I mean, this essentially came down to the second time derivative appearing in Newton's second law, right? D squared R by dt squared. So if you change from t to t prime and r to r prime, because it's a second derivative and the transformation is a linear one, this v will go away. This term is thrown out. And so Newton's second law is invariant under a Galilean transformation. We can look at it specifically for two gravitating masses. You can take the equations of motion for two gravitating masses like Sun and the Earth, make a Galilean transformation and see that they take the same form. Yeah, perhaps I will do that elsewhere. Now let us examine how the speed of a light signal behaves under a Galilean boost. Okay, so let us take a very concrete situation. Suppose that at t equal to 0, a pulse of light is emitted from the origin of S and travels along the x-axis at the postulated speed c, okay, speed of light. Then at a time t, the light pulse would have reached the location x equal to ct as per the first frame S. Yeah, it's speeding at going at speed c. But when viewed from the frame S prime, the location of the light pulse at the time t is given by x prime equal to ct minus vt. Yeah, that I'm just using this formula. X prime is equal to x minus vt, so ct minus vt, which is c minus v times t. And therefore, the speed of this pulse in S prime, and the speed is simply given by dx prime by dt prime, which is dx prime by dt, is from this formula c minus v. Yeah, because x prime is c minus v times t. So as all of you have pointed out, Rajdeep has pointed out, the speed of light in this new frame is not the same c. However, this is not consistent with the observed universality of the speed of light. I mean, if this was the case, Michael and Morley should have already found it, that the speed of light is different. Thus, the conclusion we want to draw is that Galilean transformations are not compatible with Einstein's second postulate on the constancy of the speed of light, that is, that the speed of light is the same for all inertial observers. The problem is with Galilean transformations, not with the principle of Galilean relativity. Right? So I hope this has addressed Rajdeep's question in a little bit more detail. Okay.
Yes.
Okay, thank you. So now let us talk a little bit about the synchronization of clocks, which was the question raised by Vijay and Rai, I think. Yeah, and say a little bit about this. Now, Einstein prefaced his special theory of relativity, well, following the critique of Mach, with a note on the synchronization of clocks. Okay, so we will speak a little bit about this. Now, each observer is provided with an identical clock to keep time. So all of us have the same type of clock. And now to compare measurements of time by the different observers, it is helpful if their clocks are synchronized. Okay? It's helpful if we can agree upon the time of an event. Now, let us see how far we can do this. That is, if they agree on the time of a single event. Okay, so let us see to what extent this is possible. Now, in Newtonian mechanics, as we have discussed, if a flash of light goes off somewhere, then because the speed of light is assumed infinite in Newtonian mechanics, then it arrives instantaneously at the locations of all observers. Then they can have a protocol that they will all assign the time 0 to the arrival time of that light flash. Okay? So they will all reset their clocks to read 0 at that time. Okay? Then all their clocks would be set to be synchronized, and then they will all assign the time 0 to that event. Now, this is a reasonable approximation if the speed of light is very large compared to the observer's speeds and the speeds of particles and so on. Okay? So this Newtonian approach is okay as long as speed of light is so large that it doesn't matter that it took some time for that light to reach you. But we can no longer rely on this kind of approach in special relativity, where we want to look at particles that are moving, approaching the speed of light, or of observers who are moving at speeds comparable to that of light. Okay, so we will now try to synchronize the clocks by the so-called radar method. So I mean, we did talk about radar once before, or sonar. I mean, when I said that inverse problems such as oil exploration rely upon this kind of thing. You send a signal, I mean a sound wave, into the earth, and it goes and reflects off various rocks and oil and such things, and you detect it somewhere else. And based on that, you try to deduce the composition of the earth. So, of course, it need not be in the earth; it can be in the sky also. Now, what is this radar method? In special relativity, the speed of light is finite. That is Einstein's second postulate. So Einstein proposed a radar scheme by which all inertial observers who are at a rest relative to one another. Okay, so we are starting slowly. We are now considering only observers who are at rest relative to one another. Okay, so at least for such observers, Einstein's radar scheme would assign the same time to any event. That is, all such observers who are at rest relative to each other can be made to arrange their clocks so that they can agree on the time of any event. Such a system of clocks is said to be synchronized, and this is of practical value even today, for instance, in coordinating times across the internet. Now, let me tell what this radar method is. I will explain it. I think that's about as much we can do in today's class. Okay, so suppose A and B are a pair of observers. So you and me, each of us carry the same clock, type of clock. Now, we are at rest relative to each other. Okay. Now, suppose A sends a light signal at a time TA. Okay. So sends a light signal at the time TA according to his clock towards B. Okay. Let us suppose they are only one dimension. They are both sitting along a line. A is somewhere and B is somewhere else, along the x-axis. And at time TA, A sends a light signal. It moves along the line and eventually reaches B. Okay. Suppose B receives this light signal at a time TB on her local clock. Okay, so it arrives at time TB on B's clock. Okay. All right. Now, we are going to synchronize the clocks. And how do we do this? To synchronize A's clock with that of B, what do? B immediately sends back a light pulse, maybe just reflects that light pulse back along with a small message giving the time of arrival TB. Okay, so this is what B does, receives that light signal, immediately sends it back towards A along with a message saying, I received your message at TB. So this is what B has done. Now that reflected signal will reach A at some time on A's clock. Let us call that time TA plus 2 delta. Okay, so please go through this carefully. It's very simple, but important to understand it carefully. So A receives the signal from B at some time on his clock. Let us call that time TA plus 2 delta. Okay, we are just giving a name to it. Yeah, so I will explain it in the diagram, but just before that, let me say that we will say that the two clocks are synchronized if A shifts the time displayed by his clock in such a way that TB is equal to TA plus delta. What is the reasoning for this? The idea is that the light took some time to go there and come back. And since the speed of light has been assumed to be the same independent of direction, it must have taken and the two observers are at rest relative to each other, it must have taken the same amount of time to go and come back. Okay. So we want to adjust A's clock so that the time at which B received the signal is equal to TA plus delta. So originally it may not be the case, but A will have to reset his clock such that TA plus delta is equal to TB. Remember, B has sent a message saying, I received this message, your signal at TB. Please reset your clock appropriately. So A will reset his clock so that TB is equal to TA plus delta. Now, we say now the two clocks are synchronized, and having synchronized the clocks, both clocks will assign the same time to any subsequent event. I would like to just describe this using a figure, which is called a space-time diagram. Nice way to think about these things. Okay. So in this diagram, space runs to the right, so that is the x direction, and time runs upwards. Okay, so now let us suppose that in this frame, A and B are both at rest. After all, they are at rest relative to each other, right? We have assumed that they are at rest relative to each other. So we have chosen the frame of A, for instance. Now in that frame, the trajectory of A, because it doesn't move anywhere, is the same value of x at all times. Okay, so the trajectory of A plotted in this space-time diagram will be a straight line going upwards. Okay, that is this trajectory of A. A doesn't move at all, so the location doesn't change. Similarly, B also doesn't move, so B's trajectory in this space-time diagram is also a straight line going upwards. So these two trajectories are called world lines. Yeah, world lines are basically trajectories of observers or particles in a space-time diagram. All right, now let us study what this radar scheme does. Now, at a certain time on A's clock called TA, A sends out a light signal. Yeah, light does move, so the position has to change. Yeah, and the light signal moves like this. It moves at a certain speed, constant speed. Therefore, it must travel along a straight line. Yeah, because the speed is basically dx by dt. That is the reciprocal of the slope of this line. Yeah, because t is up and x is down, x is horizontal. So the slope of this line is the reciprocal of the speed. Yeah. So 1 by slope is equal to c. Yeah. Now that light signal reaches B at some time on TB's clock, on B's clock at time TB. Then B sends it back. Again, same speed, light has same speed. So again, it must go in the same slope, yeah, in the opposite direction. And finally reach A at some later time. On A's clock, that time will read TA plus 2 delta. Okay, that is how we are defining delta. It is the time at which TA plus 2 delta is the time at which A receives the signal back from B. Then we will say that the two clocks are synchronized if TA plus delta is equal to TB. Okay, so pictorially it will mean that this and this are at the same time. Okay, so this is what it means for the two clocks to be synchronized. Now, having synchronized the clocks, yeah, we can take any other event at a later time. Now, suppose the event occurs over here, they can, both A and B can determine the time of the event through this radar method. A will send out a signal, it will go to that event and be reflected back, and then find out when it comes back. And then basically you take half of that time difference and assign that as the time of that event. And B can do a similar thing. The event may occur closer to B, spatially speaking. But does the same kind of scheme, sends a signal, radar, gets it reflected back. Because they are synchronized, they will both assign the same time to this event. So anyway, I encourage you to sit by yourself with this kind of diagram and understand how these lines are drawn, what is their slope and such things, and what it means for the clocks to be synchronized. Okay, so so I think I am now also out of time. So we have just begun our discussion. Yes, please.
So, from here, I think the time dilation formula follows, right? Like from this diagram.
See, time dilation is a related concept, but for that you need two observers in relative motion. Right now, we have not allowed for that because A and B are both at rest relative to each other. Okay, so
we can consider a stationary reference frame, like who is observing this thing from outside at rest and seeing that the beam of light is taking, with respect to this moving particle, taking t plus 2 delta t. But for that who is in the stationary frame, he would just say that the distance between AB, that is AB by C, that would be the time for him, and the difference is the time dilation.
Sure, you're right. We can add a third observer who is moving relative to A and B, and I think you are referring to that. So one can develop a concept of time dilation from this. We will do that after a little bit of time. So just hold on. After we discuss this simultaneity and so on, we will go to the concepts of Lorentz transformations and then time dilation. But yes, please.
Excuse me, sir.
Yeah.
Sir, could you once explain with what would be the diagrams if the times were not synchronized?
No, see, in this, there is no assumption of synchrony yet. In this diagram, we have not synchronized the clocks. This TA is some time according to his own clock. This is some TA plus 2 delta. So this is 2 p.m. today, this is 4 p.m. today, and this is going to be 3 p.m. today, according to my clock.
Sir, I was talking about that event E.
Okay, but I don't think it makes too much of a difference. But one moment, see, we will say that the two clocks are synchronized only if TB is equal to TA plus delta. That is the act of synchrony. If that is not the case, they are not synchronized. And in the second diagram here, I have assumed they are synchronized, and that's why I have labeled both as TE. Otherwise, it will not be the case. Okay. What you are saying is that there is some TA here, and then there is some TA plus something, or I can call it 2 delta. And then half of that difference, which will be TA plus delta, will be the time that A assigns to the event E. Now B will do something similar. There'll be some TB and TB plus 2 delta prime and so on. You will get such a diagram. I think that is what you are speaking about.
Sir, I mean, if they were not synchronized, will that T be up or down like that? The T for B.
No. They will not be up or down. That is not the thing. No, that is not the case. It is just that the reading on A's clock will not match the reading on B's clock that B assigns to the event E. See, both A and B are going to assign some time to the event E. A is going to assign the time TA plus delta to the event E. Similarly, B is going to assign a certain time to the event T, which is given by TB plus delta prime. The figure is not going to change. It is just that the time the two assign will not be the same. But that can be fixed by resetting A's clock so that the two agree. for one event. That's all. That's all we are saying. The picture will not change.
Okay, sir.
Sure. Yeah. It takes some getting used to. Next time we will draw yet more another diagram with the slightly different situation, and I hope that will you will get a little bit more comfortable with these diagrams. I mean, there is a caption to this diagram where this is explained briefly. I encourage you to read it also. Okay. Any other? Oh, there is something in the chat box. Milan Paul asks, can you explain homogeneity of space and homogeneity of time once again? Okay, that is a different concept, but yeah, homogeneity of space was the proposal, which goes back much more. I mean, it is nothing to do with special relativity. It is the proposal, it is the observation that there is no distinguished location. So this is a precursor to Galileo's principle that there is no preferred inertial reference frame. This is an even more basic principle that the results of experiments done in Kolkata. Where are you located, by the way, Milan Paul?
Sir, Kerala.
Oh, Kerala. Okay, okay. I should have said Kolkata. Yeah, you are in Kerala. Sorry, which town?
Kochi.
Kochi. Okay. So the results of an experiment performed in Kochi and that same experiment performed in Chennai should be the same provided external conditions are the same. That is, I should maintain the same temperature that you maintain. Yeah. And indeed the conditions, external conditions should be the same. Like there should not be that the experiment should not depend on the minute difference in the acceleration due to gravity between Kochi and Chennai. Okay. So assuming external conditions are the same, yeah, then the results of experiment should be the same no matter where they are performed. This is the statement of homogeneity of time. Sorry, homogeneity of space. Is that clear?
Yes, sir, it's clear.
Yeah. So in a very concrete way, this is what it means. It means, so in a more colloquial way, we will say that all places look the same. Yeah. Physics at all places is the same. The laws of physics are the same no matter where you are. Or physics laws obey translation invariance. If you translate your position, the laws of physics don't change. Okay, so these are different ways of stating homogeneity of space. Now your second, so is that okay for homogeneity of space, Milan?
Yes, sir.
Oh.
Sir, for time, the same
Yeah.
thing is.
Yeah, a very similar thing.
Okay.
Very similar thing. We may state it slightly differently. That homogeneity of time means that the results of experiments given the same external conditions do not depend on when the experiment is performed. I can do it today in Kochi, or rather you can do it today in Kochi or after 3 days in Kochi, provided the external conditions are the same. That is, your experiment is not dependent on the change in temperature between now and 3 days from now. Yeah, provided such external conditions do not change, the results should be the same. Yeah. So this is, of course, a very, very important principle of physics. Yeah, that this is called homogeneity of time. There is no distinguished zero of time. You can do it today, tomorrow, day after, you should get the same results. Yeah, I emphasize it does not hold if you change external conditions. Yeah, I mean, if your experiment depends on the presence of a cyclone or not of a cyclone, then no wonder it will depend on whether cyclone is present today or not present day after. Yeah, so we are not discussing that. If external conditions are the same, then results of experiments are the same no matter when they are performed. We can say it in a different way also. We can say that laws of physics are time translation invariant. If you shift t to t plus delta, then the results of the equation should not change. The equations of motion should be unchanged, and the results of physical laws or the physical laws also should not depend on that delta. This is homogeneity of time. Some people will state it also as saying the results of experiments are reproducible. If you do it today, you get some result. 3 days from now, somebody else does it in the same place with the same external conditions. Do they get the same results or not? Answer is yes, they do get the same results, and therefore we believe in the homogeneity of time. Is that okay?
Yes, sir, it's okay.
All right. Okay.
So
Yes.
in your second wall line diagram thing,
Yes.
The reason that A sends a ray before the event E occurs is that A is continuously sending rays, and
Yeah.
only one of them returns.
Yes. So yeah, no, I mean, if you have a particular event of interest, we have not talked about causality very much, but yeah, to go and study when it happened, you have to have sent a signal to it before it happened. Yeah, so in principle, A has to be consistently sending out signals all the time, and in the hope that the signal will go to an event of interest and come back to A. Indeed. Yeah, if the event happened even before, we will have to look at the A's world line at an even earlier stage and then send a signal to it. Is that what you're referring to, Romit?
Yes, so I was assuming that there would be like more lines branching off from A and just going off into beyond B.
Correct. Yeah, A would be sending signals all the time. If
Yes.
if A is in this unpleasant business of keeping on looking for events, yeah, then yeah. So A has an antenna that is sending out waves all the time. Some waves go to interesting events. Some just go and don't come back. Things like that.
Okay. So
Okay. All right. So any other questions right now? Yeah. All right. So in that case, we shall continue on Tuesday next week. I wish you a good afternoon and weekend. And we shall meet next Tuesday. Thank you very much.
Thank you, sir.
Thank you,
sir.
Yeah.
Thank you.
Thank you.
Thank you, sir.
Yeah.
Thank you.